So after discussing the counting principle, it leads very nicely into the permutations and combinations section. So, all right, so let's talk about ordering. So how many ways are there to arrange the letters A, B, C, and D from left to right? So you have four distinct objects. I'm just going with letters here. It doesn't really matter. So we could do this with the counting principle already. So this would be a problem that hopefully you're already able to do. So you have four options for what's going to be the first letter that you write down. So maybe you put a B down. And then after you put the B down, well, you can't do B again. So maybe you do D after that. But really, you only have like three options left. After this, you have two options. It could be A or it could be C. Let's say that you do go with A. And then you have one option left. You're at this point, in this example, you're stuck with C. Right, so there are 4 times 3 times 2 times 1 possible options. This is equal to 24. This right here, 4 times 3 times 2 times 1, this is an example of a factorial. So n factorial is the product of the whole numbers n through 1, and we symbolize it by n with a little exclamation mark. So n exclamation mark, we read this as n factorial. N factorial is equal to n times n minus 1 times n minus 2 times ... down all the way down to 3 times 2 times 1. So we, in the previous slide, wrote down 4 factorial. I could do like 7 factorial would just be 7 times 6 times 5 times 4 times 3 times 2 times 1, and so on. So 11 factorial starts at 11 times 10 times 9, and it goes all the way down to 1. Okay. Key point here is that n factorial is equal to the number of ways that we can arrange n distinct objects. So in the A, B, C, and D example that we started with, there were 4 factorial ways to rearrange those 4 distinct objects, or letters in that case. All right, so here's a seemingly stupid question. How many ways are there to arrange just a single object? Well, there's just one way to do it, right? So 1 factorial should be equal to 1, right? Because, if you're saying how many ways are there to arrange just like a single letter from left to right, there's only one way to do it. There's nothing to do, so you don't have to do anything. So this is very stupid, yeah, no, duh. But let me ask you this. How many ways are there to arrange 0 objects? Okay, so think about it. If you're trying to arrange 0 objects, like your mom tells you to go to the shelf and put all of the unicorns on the shelf from, arrange them from left to right. And there aren't any unicorns. So, how many options do you have for what to do in this situation? There's only one option. You don't have to do anything, right? So how many ways are there to arrange 0 objects? There's only one thing that you could do, and that thing to do is nothing. So there is only one way to arrange 0 objects, and so 0 factorial is actually equal to 1. So this is this weird sort of oddity about factorials, that 1 factorial is equal to 1 because there's only one way to rearrange one object, and also 0 factorial is also equal to 1. So 0 factorial, we can't really define this in the same way as we do other factorials. So 2 factorial is equal to 2 times 1, and then we stop at 1. 0 factorial, we can't really do the same thing. We just have to kind of make sense of it using this fact and the fact that there's one way to arrange 0 objects, and so 0 factorial is very commonly recognized to be equal to 1. Okay, permutations are just arrangements of objects in a definite order. So in the first example, the A through D example, we were looking at permutations of the letters A, B, C, and D. So how many permutations of, A, B, and C are there? Well, let's just kind of list them out. So you could just do A, B, C, or maybe you could swap the B and the C, or maybe B goes first, and then either A could go second or C could go second, or maybe C goes first, in which case you could either have A go second or B go second, and this accounts for all possible options. So these right here are the 6 possible permutations of the letters A, B, and C, right? So, counting permutations, like we've already kind of known how to do this. Well, you have 3 options for the first, 2 options for the second, and then 1 option for the third. And so n factorial, or 3 factorial in this case, is equal to the number of permutations of the 3 distinct letters. And so, yeah, so you could define n factorial as like the number of permutations of n distinct objects. So 3 factorial is the number of permutations of 3 distinct objects. 7 factorial is the number of permutations of 7 distinct objects, which is, just rearrangements of an object in some order, where we're like specifically saying like this order, the order matters. Okay. Sorry, this keeps the slides like keep skipping on me for some reason. All right, so let's revisit an example that we did in the previous video. So let's suppose we have a class of 12 students and we want to know who the 3 tallest students are. How many possible outcomes are there? So we already did this, so I'm going to go pretty quickly here. So you have 12 options for who's going to be the tallest student, right? So, and then once you decide who's the tallest, well, how many options are there for who's going to be the second tallest? You have 11 options for who's second tallest. And then you have 10 options for who's going to be third tallest. So you get 12 times 11 times 10, which is equal to 132 times 10, or 1,320 total possibilities. Okay. Here's another way that we could have thought about this problem. So you could just say that you're like rearranging all of the 12 students. So first, how many ways are there to like order the 12 students according to, who's like the first tallest to second to third, all the way down to who is the shortest, right? Who is the 12th tallest. So if you're counting how many possible outcomes are there for who are the, what is the order of the 12 tallest students, that would just be 12 factorial, which is 12 times 11 times 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. Okay. Okay. Obviously, this is like overcounting by a lot, but whenever, so in combinatorics, a lot of times what ends up happening is you try to count something and then you recognize that the way that you're counting it is overcounting by something, and then you just either cancel out that overcounting either by like subtraction or division, depending on like what the like how, in what way are you overcounting, just to compensate for it. So let's do that here. So in this example, here we picked out like the 3 tallest students, and then these right here are like the next 9 tallest students, or the 9 shortest students, right? So if you're trying to decide who are the 3 tallest students, you don't actually care about who are like the 9 shortest students. So this over here, so this right here is just 9 factorial. The 9 factorial, you could just cancel it out to be left with the 12 times 11 times 10, because you don't care about the ordering of those 9 students. So just divide by that 9 factorial right there to cancel all that out and be left with our actual answer. So what we have right here, by the way, this is not 12 factorial anymore, so I'm going to erase that. So this right here was basically 12 factorial over 9 factorial. And this would be like perhaps a more compact way of writing what we have over here. And this we can kind of generalize to like, okay, what if we had like 53 students and we wanted to know who the 10 tallest students are? Well, then you could just say, so there are 53 factorial ways to arrange those students. And then what's 53 minus 10? So you do 53 minus 10, which is 43, and do like 43 factorial to say that you don't care about like what the 43 shortest students' heights are. So 53 factorial over 43 factorial. And this would be a compact way of writing that answer, right? If you didn't do this, then you would have to write 53 times 52 times 51 times 50 times 49 times 48 times 40, blah, 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 until you get to 44. It's just kind of like more annoying to write that. So, okay, so this is like a thing. So permutation formula for distinct objects. So the number of permutations of n distinct objects selected k at a time is exactly what we just did in the previous slide. It's we denote it by p of nk. P stands for permutations. N is just the number of distinct objects that you're caring about the order. And then k is like, well, you're choosing k of those. So like in the previous one, we had 53 students. We want to know who the 10 tallest students are. So n was 53. You're picking 53 distinct things, and then you're picking them out 10 at a time. You're picking the 10 tallest students, and then you're left with n factorial over n minus k factorial, right? N factorial over n minus k factorial. Yeah, cool. All right, so playoffs. So let's say that we have a league with 16 teams and the top 7 teams make the playoffs, and the seedings are going to be based off their records. So like, the seedings is just like who is the best team, who's the second best team, who's the third best team. It's just an ordering of the top 7 teams. So how many possible playoff seedings are there? In other words, how many possible orderings of the top 7 teams in this league are there? So we can now, using this permutations of n distinct objects selected k at a time, just use that formula to just say, well, so there are 16 things that we're choosing from, and we're picking the top 7 teams. So that's going to be 16 factorial over 16 minus 7 factorial. So you could write this as 16 factorial over what's 16 minus 7. That's equal to 9 factorial. And that would be the number of playoff seedings that there are. If you wanted to compute this, you could, from here, actually write this as 16 times 15, 14, 13, 12, 11 times 10. And then everything from 9, 8, 7, 6, 5, 4, 3, 2, 1, those are all going to get canceled out. And so if you wanted to actually put this into a calculator, this is probably how I would do it. Let me actually see if I write into like Google, because I just use Google for my calculators all the time. If I write 16 exclamation mark over 9 exclamation mark, it actually does calculate it for me. So 16 factorial over 9 factorial is equal to 5765760. So just this number right here. That's how many possible playoff seedings there are. Okay. Permutations of indistinguishable objects. So let's now say how many permutations of the word sisters are there, and then we'll build up to something a little harder, which is the word announcement. So the word sisters, the tricky thing with this is that there are 3 S's. So if I just had, so how many letters are in the word sisters? S-I-S-T-E-R-S. So there are 7 letters, right? And 3 of them are S's. So if you just had 7 letters and you wanted to take a permutation of those 7 letters, then there would be 7 factorial possible permutations of that 7-letter word, right? So maybe we write one down. Maybe you do ISTSSRE. Yeah, okay, so that one works. But like, you know, if someone else were to say like, okay, well, let's say that like this right here is the first S, this is the second S, this is the third S. If someone else were to have rearranged those 3 S's, it would be completely indistinguishable, right? Like if you were to swap this S and this S with each other, like you still get the same exact permutation, because you can't tell the difference between 2 S's, right? And so if I were to just write down 7 factorial, this would be overcounting by a lot, because it's forgetting the fact that there are 3 S's here. There are 3 letters which like we don't know or care what the difference between those 3 S's is. And so what we actually have to do is divide out by, so for every one of these permutations, there's going to be, so let's say that this is like S1, this is S2, and this is S3. So I could rearrange those 3 S's. Let's say that someone can tell the difference between those 3 S's. So you could do I, S1, T, S2, S3, RE. Or you could do something different where like you do S3, S2, or you could do, maybe you do S2, S1, S3, 2, 1, 3. Right, okay, so you're gonna have like a bunch of different permutations that all look the same, but they're all just literally gonna be whatever this thing is. And how many different ways are there to do this? Well, you know, you're just rearranging 3 objects. So you're taking permutations of the 3 S's. How many ways are there to rearrange the 3 S's? Well, there's 3 factorial ways to rearrange those S's. So the number, so we have to just divide by that 3 factorial to account for this. Okay. And so, yeah, there would be 7 factorial divided by 3 factorial ways to count permutations of the word sisters. All right, well, let's do announcement because this is going to be a little bit harder. Put that off to the side. So announcement, let's count how many letters. 1, 2, A-N-N, O-U-N-C-E-M, E-N-T. So I'm counting 12 letters. And then I'm just going to count like each letter as they come up. So A-N-O-U-C-E-M-T. Okay, so how many of each letter is going to come up? So A shows up once. N shows up 1, 2, 3, 4 times. O shows up once. U shows up once. C just once. E just once. M just once. Hold up. Sorry, I forgot the E. There's multiple E's. There are 2 E's right here. 2 E's, 1 M, and then 1 T. Okay, so let's double check that this adds up to 12. 6 right here. 1, 2, 3, 4, 5, 6. Okay, so this adds up to 12. So this is a good count right here. Potentially, I guess. And so if we wanted to take permutations of those 12 letters, so if we could tell the difference between all of the N's and all of the E's, then it would just be 12 factorial total permutations. But we're going to have like groups of permutations where we have like the 4 N's could be like any permutation of those 4 N's, like we don't care about. So we divide by 4 factorial because there's 4 factorial permutations of the N's. And then we also want to divide by 2 factorial because there's also permutations of the 2 e's that show up. So we divide by 4 factorial, and then we also divide by 2 factorial to account for the permutations of the e's and to account for the permutations of the n's. And so this would be our answer for how many permutations of the word announcement are there. Okay, let's transition. So let's say that a professor is giving 10 possible short answer questions on a study guide, and they tell the class that 3 of those questions are going to show up on the exam. All right, how many possible outcomes are there? So, we might think of it like this. So, let's say that like we care about like the order. So let's say that we're picking. Let's say that like we wanted to know like what was problem 1, what was problem 2, and what was problem 3 that showed up on this. Well, this would just say, well, we're picking from 10 things the first 3 questions that are going to show up on there. And so this would be 10 factorial over 10 minus 3 factorial permutations, right? So it would be like you have 10 options for what's going to be the first thing that shows up on the study guide, 9 options for what's going to be this, the second thing that shows up on the exam from the study guide, and then 8 options for what's going to be the third thing that shows up on the exam from the study guide. Right? So what's the problem with this? The problem is that, you know, if you're just like looking to see which of those problems are going to show up on the exam, you don't realistically care like what's going to be problem 1, what's going to be problem 2, what's going to be problem 3. Like if I were to say like question 1 is the one about the permutations, question 2 is the one about the graphs, and question 3 is the one about percentages, then like, and for all intents and purposes, like if I were to reorder those, to rearrange them, just, you know, switch the order of like what comes first, second, and third, that doesn't affect you at all because it's like, you know, did you study for the problem or not? You don't care about the order. And so you actually want to divide by those possibilities because you like want to treat those possibilities all as the same. So there are, well, okay, so let's say this was like the one about percentages, this is the one about permutations, and then this is the one about graphs. So this count over here, 10 times 9 times 8, this is accounting for, you know, this would say that like this ordering right here would be, this ordering right here would be different from the ordering over here where I like do something like this. But we want all of these like things to be the same because it's just like, okay, these are the 3 things that come up on there. So, okay, well, how many permutations of these 3 questions are there? Well, there are 3 factorial, so let's just divide by 3 factorial on this. So our actual answer is going to be, you know, 10 factorial over 7 factorial. That's what this was. But we also divide by 3 factorial. And this right here is called, we could actually denote this as, so this is called a combination. So we're choosing things. So this is like 10, so we have 10 things, and then we're choosing 3 of them, and we don't care what the order is. So the number of combinations of n objects where we're choosing k of them at a time, in particular, where we don't care about order, we don't care about order here, this would be the following. So you just take p of nk, but then you just divide by k factorial because, well, you chose k things, but you don't care what order they come in, so you just take number of permutations of those those k things chosen from the n objects, and then just divide by k factorial, because the permutations of those k objects are all effectively the same to you, and so this is how many combinations of n objects chosen k at a time is. Okay, so let's apply this. So let's say 10 of Jonas's friends want to play volleyball with him. Say Jonas needs to pick 5 of his friends to be on his team. How many ways are there for Jonas to pick out his team? Okay, well, here again, Jonas doesn't care like the order in which he picks out his friends. So like he just cares who's going to be on the team. And he's not saying, oh, you're the best person that I'm picking, you're the second best person that I'm picking. He doesn't care. He just cares about who's on the team, who's not. So that would be he's taking 10 out of 10 friends, he's choosing 5 of them without caring about the order. So this would be 10 factorial over 10 minus 5 factorial times 5 factorial. Okay, so we could, of course, simplify this to 10 factorial over what's 10 minus 5? It's just 5 factorial, and then times 5 factorial. If we wanted to simplify this a little bit more, 10 factorial is 10 times 9, 8 times 7 times 6, then times 5, 4, 3, 2, 1. But then it's like still over 5 factorial, so we cancel out a 5 factorial with a 5 factorial over here, and then we're still left with this. But I don't know, that doesn't really seem super helpful to me, so let's maybe just leave it like this. Okay, so we'll leave it like that. You could put that into a calculator to figure out what that is equal to. If your calculator doesn't have a factorial button on there, like a lot of scientific calculators don't, that is the point where you would do what I had before right here. Just do this divided by 5 times 4 times 3 times 2 times 1. Okay. And then you can kind of see like how this would generalize too. Like what if Jonas had like instead of 10 friends, let's say that he had 15 friends, and then he needed to pick out like let's say 6 of them to be on the team. Then this would be 15 factorial over 15 minus 6 factorial. So like at this point, this is just number of permutations, and then times 6 factorial. And this would be, we're dividing out by the permutations of those 6 friends that are on the team, because we don't care in which order we pick the friends. All right, here's another one. Let's say that 20 of Jonas's friends want to play soccer with him. Let's start saying that like we care about like how many are boys, how many are girls. So let's say that 11 are boys and 9 of them are girls. And Jonas needs to pick 10 of them to be on his team. And let's say in particular he wants 4 of those 10 to be boys and the other 6 to be girls. Maybe there's like some like maybe he's like in a co-ed league and like they have like restrictions on like how many boys and how many girls are going to be on the team or something. Okay, so how many ways are there for Jonas to do such a thing? Well, there are 11 boys and he wants to pick 4 of them to be on the team. So from those 11, if he's picking out 4, that would be 11 choose 4 total possibilities to pick out the 4 boys for the team. And then we could actually apply the counting principle here. So we could say like, all right, well, this is how many ways there are to choose the boys to be on the team. And how many ways are there to choose the girls on the team? Well, there would be 9 girls, and he's choosing 6 of them to be on the team. So there would be this many ways to choose boys to be on the team, this many ways to choose girls on the team, and we could just take those numbers and multiply them together. So what's 11 choose 4? That's 11 factorial over 11 minus 4 factorial times 4 factorial. And then this is times 9 factorial over 9 minus 6 factorial times 6 factorial. We could simplify this to 11 factorial times 9 factorial over 7 factorial times 4 factorial times 3 factorial times 6 factorial. Admittedly, this is not that much simpler, but you know, perhaps slightly better. I'm not going to go ahead and put this into a calculator. I'm just going to say this is a fine enough answer for now, and you know, you could kind of simplify things and write them out as a product, or if you like type things into Google Chrome will, like, if you type in like 16 exclamation mark, it'll calculate 16 factorial for you. Like, you could use like a Google Chrome's calculator functionality if your scientific calculator is not really working for you. Yeah, okay. Yeah, and that's it. So hope this helped, and see you in the next one.